Morning, this is Ms. Billerbeck, and we're going to talk about 5.4 transformations of piecewise-defined functions. So if we have floor functions, we can write those with our technology. For instance, a graphing calculator is one of these. I like the TI-84 Plus. And then we also have we can use FloorX on Desmos, our online graphing calculator on our computers or PCs or Chromebooks. All right, so let's take a look at what that looks like on the graphing calculator. So if we turn it on, so we have to turn it on, okay, and then we're going to go to Y. Now let me clear that so you can see how I put that in. So I'm going to go to this button called Math, and then I'm going to go to Numbers. So I'm going to arrow over to the number, and I see I have INT is number 5. I can either arrow down to number 5 and hit Enter. Whoops. There we go. Or I can just put in number 5 and it pops up. So I want to be in the Y equals mode here because I want to plot it. So I've got int, and I have a parentheses, but I need an X. So we see there's an X in green right above the store key. So I'm going to hit the green key, alpha store, and it gives me the X. And now I'm going to end parentheses. So this should show me a floor function when I hit graph. And the graph button is here on the graphing calculator. So I hit graph and I see a nice step function for a floor function. Okay. Now if I want to do the ceiling function, we remember from the former lesson we saw that the ceiling function was just one larger than the floor function. So if I go back to the Y equals key here, and I go down and I add math, and this time I'm going to hit the arrow to numbers, and I'll just go down to 5 and hit enter there to do the int. So then alpha, and then the store key has a little green X above it, and then parentheses, and then I'm just going to do plus 1. Okay, so let's see if that will graph any differently. Oh, look, it just made it a teeny bit wider because it's two different graphs. Okay, so one graph's right next to the other. All right, so these are the way that the ceiling and the floor function can be used to be graphed on this graphing calculator. Okay, so again, if you wanted to see, if we just go to Y equals and we delete this by marking clear and then hit graph, we see, oh, we just have the floor function. Before we had the floor and the ceiling function, which doubled it up. All right, so that's the graphing calculator. And let's take a look at what in a moment what the Desmos will do. And then we'll get into an example of how to do a floor and a ceiling function. So let me share the screen. All right, so when we do Desmos, if we mistakenly, we don't have to do Y equals, but if we put in INT by mistake, we get an integral. Yikes, that's why they can't do int on Desmos. Okay, so we type in floor or floor function, and then we just write in X like that. Whoops, something interesting just happened there. There we go. So we see we have a floor function. Okay, so floor function rounds down. So this point would be part of it, but this point would not. So the problem with this graphing calculator is it's not showing the open point. Okay, now before we saw the ceiling function on the graphing calculator being right next to the other one. So fortunately on Desmos, it plots these in different colors so we can see it. So we just spell seal, not ceiling, just seal. And there we have it. So the blue ceiling function is right next to the floor function. So it's rounding from -1 to 0. So this would not, the -1 would not be included here, but 0 is. The -2, the 0 would not be included, but the 1 would be, as opposed to the floor function, which that would not be, that would be included on the red, and then this point here would not be included. Okay, so feel free to play around with Desmos on this, with the floor and the ceiling functions. All right, so let me stop the share and we will get into our lesson. So many of us are in programs where they have bonus points. So as a business, you want to advertise that you're giving away bonus points, but as a business, you want to make a profit. Otherwise, you wouldn't be in a business. So you want to make it sound good, but make it as minimize the good so you get more profit. So in this case, when you do this, we're doing a floor function, so we round down. So that's minimizing what the consumer is giving us in money. So if we have Uptown Sandwich Shop is decreasing its bonus points by 2 points, how will the total points be awarded for a $1.25 juice drink if the original reward points are defined by f of x equals the floor function of x plus 5? Well, if we're reducing our rewards points, then the new function f1 of x, or why don't we just call it g of x, just so we know it's different. So we're going to have our new function g of x equals int and then x. But we're going to reduce this so it's plus 3. So what this means is for $1.25, our rewards points would be for the f of x. So f of $1.25, the output would be 1, because we rounded down to the 1, plus 5, which would be 6. But if we had g of 1.25, we would have this one would be rounded down to 1 plus 3 would just be 4 rewards points. Okay, so you can see how rounding down gets you a little bit more profit there. So that's why it's used more in business situations. All right, so if you ever wanted to know why there's a floor function, there you go. All right, so let's take a look at our absolute value function again. So we started out this chapter with absolute value functions as very special piecewise defined functions. But now we're going to actually look at the anatomy of an absolute value function. So when we write it in this way, it's similar to vertex form of a parabola. So I like to see it in this form because this is the form that you're going to see for parabolas, for logarithms, for trigonometry. So it's a very consistent form. So once you get the idea of how this works in this medium, you should be able to learn the others very quickly. Okay, so we have y equals a variable a times the absolute value of x minus h plus k. So this A is responsible for stretching or compressing. So stretching means it's going to be closer to the y-axis if it's stretched toward the y-axis, and compression if it's compressing away from the y-axis and toward the x-axis. Okay, and then if it's less than 0, if it's a negative number, that reflects it across the x-axis. So I'll show you that some more. But this gives us a vertex at h and k. Now, please note that this is a negative sign. It's very unusual. And this is a positive sign. So this is the one that really catches a lot of people by surprise when they're trying to find the vertex, because they'll put the negative with this. But it needs to be negative for a right shifting horizontal shift, and or it needs to be a minus and a positive number for a right shift. And if this is a negative number, then it would shift left. So this k here is just pretty straightforward. So if it's positive, it's up. If it's negative, it's down. Okay. If we have a vertex, the axis of symmetry always goes through that vertex. So we know that if it's a horizontal line, we define horizontal lines by what value of x it is going through. So that's why h is the definition of this axis of symmetry. So x equals h. It's the vertical line going through that point on x. All right, so let's take a look at Desmos and just play around with Desmos for just a tad so you get comfortable with what is going on with this. All right, so if we have the absolute value screen, we see we have y equals a times the absolute value of b, x minus c plus d. Okay, so I didn't use the hk, so let me just switch this over to h and this one to k. Okay, and let's get rid of c and d. Okay. And we also, B, we're going to get rid of because we're just not going to deal with B right now. You will someday, but let's make it as simple as possible. So that's what we're looking at. So we can see that H, if H is 0, and K is also 0, we see we have the parent function. Okay, A is 1 as well. So this at 2, we're going through 2. At 4, we're going to 4. This is exactly the parent function. Now, let's see what happens if we just move A. So as we stretch it, A is greater than 1. So watch how these lines get closer to the y-axis for a vertical stretch. So that's a vertical stretch. Whoops. Sorry, I have a temporary computer, and this is not as nice as my other one. Okay, at 0, it just zeroes everything out, so there's really nothing going on. But let's go in here, just in the decimals. So these are the fractions between 0 and 1. So we see that it's getting farther away from the y-axis here, so, and closer to the x-axis. So it's stretching toward the horizontal axis, but compressing away from the vertical axis. So if we just memorize one of the axes, the other axis is the opposite. So if we memorize the vertical axis, when it's less than 1, between 0 and 1, it's a vertical compression. When it's greater than 1, it's a vertical stretch. And then the horizontal is just the opposite. Let's get this back to 1. There we go. All right. So now we're going to work with this h. What does h do? So as h moves into the positive range, we see that the parent function is just shifting to the right. As we move to the negative range, which a minus minus makes a positive, so that'd be x plus 7.1 or x minus negative 7.1, we see it's shifting to the left. Okay, so let's put that back to 0. Now let's see what k does. As k is positive, it raises the parent function up. As it becomes negative, it raises the parent down. Takes the parent down. Whoa, what just happened? Well, let's just take a look. There we go. Might as well use the animation since it popped up. All right, so that's one great thing about Desmos is the animation. Okay, so that's what all these do. So let's just go ahead and animate away. Let's see. Will it do it? Nope, it's just, oh, here we go. Now it's doing it. So there you go. Oh, look at the nice little square it's making. All right, and if we want to animate this, we can do that too. So there you go. Now it's flying. Whoa, I got a little small. There you go. All right, so that is that. How does this absolute value function work? So let's go ahead and stop the share and get back to our lesson. Okay, there we go. So for this one, we have for each function, let's identify the vertex and the axis of symmetry. So just by looking at this and remembering what we were looking at before, if we have y equals a, and we have the absolute value of x minus h plus k, and we know the vertex is hk. So let's keep that in mind. Let me find a different pen that has a prettier color there. Okay, so this one, if we look at that, p of x actually has a 1 in front of there, and we have x minus 0 plus 3. So our h is right here, and our k is right here. So our vertex for this would be at 0, 3, and our axis of symmetry is a vertical line going through h. So h is 0, so it's x equals 0. Okay, so let's look at this one. We have g of x equals, again, a is a 1, and we have the absolute value of x minus 0 plus a negative 2. I changed that minus sign to a plus negative so we could emphasize where this vertex is. So we are at 0, negative 2 for our vertex, and our axis of symmetry is still going through this h right here. This is h, this is k. So we have x equals 0. So again, our axis of symmetry is where it folds where you can fold one graph over the other and it'll just overlap. So that's the axis of symmetry. Okay, now let's take a look at this one. So we have h of x equals 1 times x minus 3 plus 0. So our h is, and our vertex is 3, 0. Our axis of symmetry is x equals 3, because that's what h is. Now this one's a little tricky, so let's look at it. T of x equals 1. We have x minus a negative 5 plus 0. So our h is here and our k is here. So we have to remember it needs to be a minus. This is a huge error to make that a plus 5. I know we want to, but don't do it. Okay, so h is negative 5 and k is 0. And our axis of symmetry is going through negative 5. So x equals negative 5 is our axis of symmetry. Okay, so that one just didn't want you to graph. So this one does want you to graph. So find the vertex of the graph, at vertex, and graph each function. So when we look at this again, like we did the other functions, we have 1 times x minus 1 plus a negative 3. So we have h here, k here. So our vertex will be at 1, negative 3, and our axis of symmetry will be x equals 1. So we see we're shifted over 1 to the right. Okay, this particular one, we're going to see s of x equals 1 times x minus a negative 2, and then plus 6. So this is h, this is k. So our vertex then will be negative 2, 6, and the axis of symmetry is going to go through negative 2. So x equals negative 2. All right, so let's go ahead and graph these. Okay, so our first one, we have g of x equals the absolute value of x minus 1 minus 3. So we decided that the axis of symmetry, or the vertex, is at 1, negative 3, and the axis of symmetry is at 1. Okay, we can use a chart if we're uncomfortable, or we could know that since a is 1, we just have a parent function being moved. Okay, so there's no stretch or compression because a is 1. So we can just graph the parent as is, as long as a is 1. So that means I've got a slope here of 1, so it's going to rise 1, run 1, like that. And this one will be the reflection of it around the axis. All right, if we graph, let me use a different color for this next graph. Let's use brown. Okay, so if I have s of x equals x plus 2 plus 6. We found its vertex was -2, 6, because this is a minus -2 right there. So don't get messed up by that. So we have -2 and then positive 6. So A again is 1. So we're just going to have a slope of this line of 1. So it's just going to look like this. All right, so we've translated the parent. Okay, let me draw the parent really quickly. So the parent will be in purple. So here is our parent, and all we're doing is moving it around, moving that vertex around. So this is our parent. Okay, this is S of x. And this one then is G of x. All right, so everything's very, this one's a little off on my graphing, but everything should be parallel. So if I move this back, it would line up right with the parent. If I move this up, it would line right up with the parent. So that's when A is 1. So let's look at when A is not 1. Okay, so when A is not 1, we do have a stretch going on. Okay, so we want to graph that parent again. And let's first look at where is the vertex? Okay, so we have 3 G of x equals 3, and then we have x minus 0 plus 0. So we see our vertex is at 0, 0, and our axis of symmetry is just x equals 0. And on this one, we have the similar situation. So we're just taking a parent, and all we're doing is stretching and compressing it, except this one has a negative. So that's extra special. It's reflecting it as well. So we have -1/3 x minus 0 plus 0. So our vertex is going to go through 0, 0. So we have h and a k here. And then x equals h. So we have x equals 0 for our axis of symmetry. And vertex. Okay, so let's go ahead and plot those. So these might take a little more work with charts. So let's do that. Okay, so for G of x, let's do a little chart of x and G of x. Okay, so it's always a good idea to start with -2, -1, 0, 1, 2. And we're doing that. So let's see, make a quick chart there. Okay, so G of x is 3 times the absolute value of x. So the absolute value of -2 is 2. 3 times 2 is 6. The absolute value of -1 is 1. 1 times 3 is 3. The absolute value is 0 is 0. 3 times 0 is just 0. And that's what we found, that the vertex would go through 0, 0. And the absolute value of 1 is 1. 3 times 1 is 3. Absolute value 2 is 2. 2 times 3 is 6. So we see a nice reflection going on there of numbers about the 0. So when we plot that, we have 0, 0. Our next point will be -1, 3, -2, 6. And if we use just the axis of symmetry right here, we don't even have to plot the other points, though we could so easily. But see how that's 1 away from here? Well, we know it's here because this is an axis of symmetry. And we found the axis of symmetry is at x equals 0. Vertex always lands on the axis of symmetry. So this is 2 away, so that's 2 away. So this is at 2, 6, which is what we calculated, and 1, 3, which is what we calculated. Okay, so let's graph g of x, which is 3 times the absolute value of x. And I think we've seen something like this before in our other lessons. So this is g of x equals 3 times the absolute value of x. Okay, so we see this is a vertical stretch. Otherwise known as a horizontal compression with these things. But let's leave that one off for now. Let's just call it vertical stretch so you can get an idea of what it should be. Okay, so now let's do h of x. So we have x and h of x. So this, we're going to start with -2, -1, 0, 1, 2. Okay. Oh, maybe not. Now, one thing in math is, though I usually do that, let's look at what is h of x. So h of x is -1/3 of the absolute value of x. Now, by now you must know that I don't like to graph fractions. So let's make it easy and not have fractions. So if we put multiples of 3 on here, we're safe. So if we have -3, -6, 3, and 6, now Miss Billerbeck will be much happier. So we have the absolute value of -6 is 6. -1/3 of 6 is -2. So if you didn't catch that, what I just did when I put in this -6 is I had -6, the absolute value of -6, and then I'm going to divide the output by -1 or -3, because multiplying by a -1/3 is like multiplying by -3. So the absolute value of -6 is 6. Dividing it by -3 gives me -2. Okay, if you didn't follow that, then let's go ahead and do the multiplication by -1/3. So I have the output of the absolute value -6 is 6 times -1/3 gives me a -2. Okay, so that's what I did to find that. Now, if I put in negative 1/3 times the absolute value of negative 3, that gives me negative 1/3 times 3 over 1. So we cancel, so that's just negative 1. And 0 times negative 1/3 is 0. And we know that because this is an absolute value function, it's going to reflect. But let's just do a few of these really quickly. So negative 1/3 times the absolute value of 3 is negative 1/3 times 3 over 1, which gives us negative 1, just like above. Okay? So if we did the same thing with 6, we would just get the 6 times negative 1/3, which would just be negative 2. All right. So we're going to see, because of this negative value right there, that it's going to reflect over this x-axis. So we have negative 6, negative 2, negative 3, 1, and we're going through 0, 0. Then we go to 3, negative 1, and 6, negative 2. So let's graph that one. All right, so that's what it looks like when we have a fraction. So what we're seeing here is a vertical compression because it's moving away from this y-axis. So it's compressing away from this y-axis. It's just being pushed away. But it's also a reflection about the x-axis. So it's two things going on. We've got a reflection from over here down here because of that negative. And then because it's a fraction, and it's between negative 1 and 0, it is actually vertical compression. Okay, so that's what that would look like when A is not 1. All right, so our final one. Oh, before we get to that, we were supposed to compare this to the parent function. So let's do that. So this time I'm going to put the parent function on there. So remember, it has a slope of 1 and negative 1. So here's our parent. So we can see we're stretching away from the parent here and compressing. If the parent had been reflected down here, which let's show the reflection. Because it's an absolute value, the parent never goes negative unless the parent would never go negative, but when we modify it and add negatives, then it would be where these dotted lines are. So when we look at it this way, we can see, oh yes, this purple one is compressing away from the reflection of the parent. So we have the parent function here, and this is the reflection of the parent function. And if you're not following me, what the parent function is, that was f of x equals the absolute value of x. That is the parent function. Okay. All right, let's go to the last example. We're almost done. All right, so this one, we want to write a function for this graph. So the most important thing when we're doing that is to find where is this vertex. Okay, so the vertex is right here. Okay, but that's not enough to say it's right here. So we have to look at where is right here. So this is at -1 and that's at 2. So we have the vertex is at -1, 2. Okay, so we see, let's check the slope of the function. It does not appear to be going right with the parent. The parent would be coming out like this. So we do have a is not 1, so it's a vertical stretch. So now we need to figure out, well, what is the slope? So we see, well, it's rising here, 3, and it's running 2. So it's very close to 1, but it was not. So we see a equals 3 over 2. Okay, and we have h and k. So that's all we need to write the function. So if we have y equals a times the value of x minus h plus k, we just write y equals 3/2 the absolute value of x minus -1 plus 2. But minus makes a positive, so our final equation will be with a positive. So we're going to write y equals 3/2 the absolute value of x plus 1 and then plus 2. So that would be that function right there. So now if we take this graph and we translate it, right 1 and up 4 units. Okay, so let's get some room here. And fasten our seatbelts. Could be a bumpy ride. Just joking. Okay, so we're going to move 1 unit right here, and then 4 units up. 1, 2, 3, 4. Okay, so our new vertex is now at 0, 6. Okay, this did not change the slope because it's translated. It's not stretching or compressing. It's only translating, so we moved it right 1 and then up 4. 1, 2, 3, 4. So we went from 2 to 6. So our new equation then for this will be, we'll make it g of x. I guess I should, since we're writing a function, this should be f of x to be a certified function. So we're going to write g of x equals, a is still going to be the same, 3/2 the absolute value, but now it's x minus 0 because h is 0 and k is 6. So we're going to do plus 6. So our final equation for that new translated function would be 3/2 absolute value of x plus 6. So let's graph that. So if we rise 1, 2, 3, 1, 2, that gives us our first point, and 1, 2, 3, 1, 2, that gives our second point. We only need 2 points to make a line, so we are there. So we are going to make this line right here and right here. So this would be g of x. And this one is f of x. All right. I hope that answers your questions, and have a wonderful day. Bye-bye.